Welcome to our OrangePi Peripherals Part 2. Using timers and interrupts. Plus running code with boot scripts. This episode still uses an LED, a button, and a few DuPont wires. Today we'll start by explaining how to use the timer on the OrangePi. Here, the timer's role is to make the OrangePi execute specific code at regular intervals. Let's look at the timer code. Similar to previous code, include holds.h files. src contains cpp files. Say make list is the configuration file for cmake. Main.cpp is the main program. First, let's examine tim.cpp. This code displays the elapsed time since program startup at regular intervals. This requires our timer. First, we need to set up a function to initialize the timer. Timer init. Here, we define a structure variable named timer. It has 4 structure members. The first 2 members define the delay time for the timer's first trigger. The first specifies seconds, the second specifies microseconds. So here we set the timer to trigger for the first time, after 3 seconds. The last 2 members specify the interval for repeated timer triggers. These also use seconds and microseconds as units. Therefore, our settings indicate the timer will trigger repeatedly every 1 second. Next, we initialize this timer using setTimer. If this function returns -1, it indicates initialization failed, and the program will exit with an error. If successful, it outputs timer initialization successful. Through the above code, we obtain a timer that starts after 3 seconds, and repeatedly triggers at 1 second intervals. After the timer triggers, we need to associate it with a function, so that this function is called when the timer fires. Thus, we use signal to link the timer and function. We can also see that this timer function is very simple. Each invocation increments I by 1, and outputs the elapsed time since startup. Since this function runs every second, the displayed time here matches our actual elapsed time. Next, we see the code in makelists.txt, and tim.h is actually quite straightforward. The main program only initializes the timer, followed by a while loop. Alright, let's run it and see the effect. The execution method is the same as in the previous video. Enter these commands, and it will run. If you find the text too small to read, I've also displayed the required commands on the screen. Here, after entering the password, the program starts. You can see that after 3 seconds, the screen displays how many seconds the program has been running. It then displays again every second thereafter. This achieves the function of a timer. So how do we stop this timer? Here are 2 methods. For example, if we want to stop the timer after 5 seconds, the first method is to wait until I increments to 5, meaning after 5 seconds have passed. Then set the timer parameter to 0, and reinitialize it. This stops the previous timer. Let's see how it works. First, recompile and run it again. The code runs the same as before. We'll observe what changes occur after 5 seconds. Indeed, the program halts 5 seconds after the timer starts. The second method involves canceling the association between the timer and its function. Once I increments to 5, this also achieves timer shutdown, yielding the same result as method 1. Let's fast forward to show the outcome. Now let's examine the second code, external interrupts. An external interrupt occurs when an external device triggers an interrupt signal. This signal interrupts the current program flow. After executing the interrupt function, the program returns to the original function for processing. Here, we'll use our button as the external device to generate the interrupt signal. In the code, we first configure the interrupt pin. As demonstrated in the previous video, the number 6 here refers to the pin number in wiring pi. For the actual pin number, refer to the GPIO diagram in your manual. On my board, this corresponds to pin 11. Next, we initialize this pin, set it to input mode, and enable the internal pull-up resistor. Then we need to select the interrupt mode. First, we choose the specific pin. There are 4 modes to choose from: trigger on falling edge / trigger on rising edge, trigger on either rising or falling edge, or simply do not initialize. Finally, set the callback function. When this interrupt is detected, the callback function will execute once. The variable, I, inside the function will increment by 1, and the current count of interrupt activations will be printed. The delay below prevents repeated key presses from triggering the interrupt. Actually, as mentioned in the previous code, timers should ideally be used in conjunction with interrupts. But here, I took a shortcut and used delay instead. This is just a quick demonstration of what the rest of the code looks like. Now let's run this code sequence. The execution method is identical to before. To save time, let's fast forward through it. After running the code, you can see that each time I press the button, the screen displays the number of interrupt calls. This proves it works. Lately, many friends in the group have asked me how to make code start automatically at boot. Today I'll show you how to achieve this. We'll use a tool called systemctl. With it, we can make our program run automatically at startup. Here, I'll use the boot up LED toggle program as an example. First, create a script file in this directory. Since it involves LEDs, I'll name it led_test.service. After creation, it should be an empty file. The code here is because I've already run it once. We can see its contents are exactly what's shown above. Let's break down each line. The first line describes the file. This line is for developers to quickly understand the code's purpose. The next two lines require the path to the executable we want to autostart and its directory. Here, the executable is led_test. We simply copy its path. The directory is the parent directory of led_test. For restart, enter no. We don't want the development board to reboot after the code completes. Since the LED uses GPIO, we need root privileges to control it. Finally, the wanted be line ensures our script starts automatically when the user logs into the system, enabling boot time execution. Now copy this code into your script file. With the script file ready, how do we use it? First, enter this command to update the configuration. Then enter the enable command to activate the LED's autostart service. After rebooting the computer, autostart will now function. Alternatively, you can run the start command to execute the script immediately. As shown here, after entering start, the LED begins flashing. Additionally, the status command allows checking the script's operational status. Any errors will be displayed here. If no errors occur, as shown in my current state, next, let's reboot the development board and verify if the boot up startup function succeeded. You can observe that the LED lights up the instant the system powers on. This confirms our boot up service is running successfully. Let's discuss how to disable this boot up startup. After all, we don't need to execute certain files every single time the system boots. Therefore, we see two additional commands below, one to stop the service temporarily, and another to permanently disable the boot up startup. You can observe that upon executing the stop command, the LED stops flashing.